All right. So, guys, when we started this chapter, we looked at one property which is keeping us alive. That property of acid bases, which keeps us alive, is the fact that our blood is supposed to have a fixed pH, relatively fixed pH, while we are putting a lot of acid and bases in our body. The pH of the blood is fixed, relatively fixed. The system which is keeping pH relatively fixed is called buffers. And you saw this on your lab, how when we added sodium bicarbonate to water, it made a buffer by adding acid to it, and the pH was relatively fixed. I want to give you an example. This is freshly distilled water. The pH is 7, and we are adding a drop of 1 molar hydrochloric acid. Well, let's say 1 molar, 6 molar hydrochloric acid, 6M HCl, just 1 drop. See, pH is dropped to 4. From 7 to 4, there is 3 degrees of pH change. And if I add a drop of 6 molar NaOH here, pH 7 is changed to pH 10.5. So 3.5 change of the pH. But we can make a pH 7 buffer. This is 7. We add same amount of the acid. Do you see the pH is 6.9? So 6.9, almost 7, the pH is not changed, or the change of pH is minimized when we use a buffer, while the change of pH was 3 units when we didn't have buffer. The same thing with the base. We are adding 1 drop of the same concentration of the base. pH is changed from 7 to 7.1. 7.1. We have 0.1 degree change of pH. If I didn't have the buffer, change of pH is 3.5. So what buffers are doing, they are avoiding a sudden pH change. They try to avoid pH change, the small changes. They do not cause drastic change. They avoid drastic change of the pH if you have buffer. So buffer are defined as solutions which resist a change in pH when acid or base is added. So the keyword here is resisting change of pH. And that's how our blood is keeping a fixed pH. We have 3 systems of buffer in our body, which are continuously checking the pH, adjusting the pH, trying to keep the blood pH around 7.3 to 7.4, avoiding drastic change of pH. We can die if our the blood pH is changed by 1 unit. Okay. Oops, wrong direction. So this is the pH of our blood. We need this pH. 7.3 to 7.4 is what we need to stay alive. What is fixing the pH? This buffer system continuously functioning to avoid change of pH of the blood. Now, how do buffers do that? What is the properties of buffer who can do that? Well, buffers are made from a weak acid we just said H2CO3 carbonic acid is a weak acid. It's the acid in your soft drink. So a weak acid. And the basic salt of this weak acid, did we just say Na, baking soda, NaHCO3 is the salt of the weak acid, carbonic acid. So these two, when we mix them together, they make buffer. So you need a weak acid or weak base to react with the basic salt or acidic salt of them. You might remember we talked about conjugate pairs, conjugate pairs. These two are conjugate pairs. This is the base of H2CO3. This is the acidic form. These are related together by loss of a hydrogen ion or gain of hydrogen ion. So if you take a weak acid and salt of the weak acid, you make a buffer. I'm going to the next slide. This is acetic acid, which is the acid in vinegar. It's a weak acid. This is a weak acid. The salt of this weak acid, CH3CO, Na. Do you see hydrogen is replaced with Na? The acid is provider of H+, lost its H+, reacted with base, and make the salt. So this salt and its acid, they are conjugate acid and base. Let me write it here for you. Can I say CH3COOH? And if I dissolve this in water, it's going to break down to an A+ and CH3CO minus. So can I say CH3CO minus is the conjugate base of this acid. This is the acid. And this is the conjugate base. Remember, conjugate acid base are related together by gain of hydrogen or loss of hydrogen. Do you see? If I remove this hydrogen, I get this conjugate base. If I add the hydrogen to this conjugate base, I'm going to get the acid. Actually, it's here. Weak base is breaking down. It's making, I'm sorry, this is a weak acid. I meant. Weak acid breaking down. If it loses a hydrogen, you get CH3CO minus. So this is the conjugate base. And this is the acid form. If I add a hydrogen to conjugate base, I get the acid. If I remove a hydrogen from an acid, I get the conjugate base. So mixture of these two, mixture of CH3CO minus and CH3COOH, together they make a buffer. How come the mixture of this weak acid and conjugate base how come they make a buffer? What is buffer? Buffer is a mixture which is going to avoid pH change. How could a buffer avoid pH change when we add base to it? Suppose we add a drop of sodium hydroxide, a very strong base, to mixture of these two, and this is a buffer, right? This is a buffer. Mixture of the acid and its conjugate base. Do you see these two are related together by gain of a hydrogen ion or loss of hydrogen ion? The difference between them is one hydrogen ion. So they make conjugate acid base. I have this mixture. Guys, if we add OH minus, what is going to happen? Which one of these two is going to kill the coming OH minus. Which one is going to react with OH minus? Obviously, the acid part. This part, the acid, is going to neutralize OH minus by giving H plus by making water. So amount of the acid is reduced. This is the acid form. Part of the acid was used to neutralize the OH minus, and as a result, what is formed? Conjugate base. Here, this is the acid. We added a drop of OH minus. The acid neutralized the OH minus. It makes some conjugate base. So pH is not changed. Why pH is not changed? Because this was neutralized. So any incoming base would be neutralized by the acid component. And then, what if I have this buffer? This is the buffer now, which is a mixture of conjugate base and the acid. Conjugate base of the acid and acid, 50-50. In this case, 50-50. I add a drop of acid. Acids are H plus or H3O plus, same thing. So this mixture is going to immediately neutralize the incoming acid. How? Which part, which one of these two like to react with H3O plus 1? Obviously, the negative charge. So the conjugate base is going to neutralize the acid, is going to be converted to weak acid form. So do you see a mixture of this weak acid and its conjugate base? They are continuously watching. If acid is coming, they will neutralize it. If base is coming, they are going to neutralize it. So they are watching to kill any incoming acid and base. As a result, they keep the pH relatively fixed. Now, pH changes if we add H3O plus, but the buffer is going to kill it. pH is going to change if we add OH minus, but the buffer is going to kill that. It's going to neutralize that. So we have a system which has relatively fixed pH. This is showing both of these effects. You have a mixture of the acid, a weak acid, and conjugate base. They make a buffer. You add OH minus. OH minus is going to be neutralized. You add H3O plus. H3O plus is going to neutralize. So it's a mixture of components that they would be consuming any incoming OH minus and H3O plus. As a result, the pH is relatively fixed. I think you observed this on the PLP of lab 12. You notice that we had a buffer. We added hydrochloric acid, sodium bicarbonate. It made a mixture of carbonic acid and sodium carbonate, baking soda. And then you had a buffer. You notice that when we are adding hydrochloric acid, it's resisting pH change. The change is small. When we did exactly the same thing to water, pH was abruptly changed. Okay, so go guys. What do we need to make a buffer? Remember that. To make a buffer, we need a weak acid plus conjugate base of the same acid. That means, how do you obtain conjugate base? Remove a hydrogen from acid. If I look here, is this a weak acid? Yes or no? Yes or no?
Yes.
Hydrochloric acid, stomach acid. Is it a weak acid or a strong acid? How do we know? You check the acid strength table on page 300. You get the same table on the exam. Actually, this is the strong acid. Strong acids cannot make a buffer. So the answer is no. Is carbonic acid, the acid which is in our blood, and baking soda, which has one hydrogen less than this acid. So can I say, if you look up the table, carbonic acid is a weak acid, and this has, when this is dissolved in water, it has one hydrogen less. This is the conjugate base of carbonic acid. Yes, this is a buffer. In fact, this is the buffer in your and my blood right now functioning to keep the pH fixed. Is this a weak acid? You check the table. Phosphoric acid is a weak acid. Is this a conjugate base of this acid? In other words, does this have everything except one hydrogen less? Obviously, no, they don't relate together by loss and gain of hydrogen. So this is not a conjugate base of this acid. So this does not make a buffer. Is this weak acid? That's the acid in vinegar, acetic acid. Yes, this is a weak acid. Is this containing one hydrogen less? You see hydrogen is replaced with K. So this is the salt of this acid. This is the conjugate base. Mixture of weak acid and its conjugate base makes a buffer. So that's the answer. No, because this is a strong acid. Yes, because this is a weak acid, and this is the salt of this weak acid. Weak acid, but this is not salt of this weak acid. It doesn't have PO4 in it. Weak acid and the salt of weak acid. Yes. Any question? Anybody? All right. Guys, in some chemical reactions, we need to have a fixed pH. That means some chemical reactions need varieties of fixed pH. You can have fixed pH of 2. Some enzymes in our body needs the fixed pH of 2. Some need pH of 7. Some chemical reactions need different pH. So we can make buffers which can keep the pH fixed, but the value of fixed pH may not be 7, may not be 3, may not be 5. So we can make buffers which have all sorts of fixed pH, pH 2 buffer, pH 3 buffer, pH 4 buffer, pH 7 buffer, pH 10 buffer. How do we make a buffer of varieties of fixed pH? How do we do that? So we are going to use this concept of equilibrium constant, which we discussed on chapter 6. So we said a buffer is made out of a weak acid. That's one of the components of a buffer system. What do we call a weak acid? What was the definition of a strong acid and weak acid. Weak acids do not ionize 100%. Equilibrium, weak acids are partially ionized, partially dissociated in water. What does that mean? That means the weak acid that we're talking about, it ionizes in water, it produces hydronium ion and its conjugate base, but partially, not 100%. So we have an equilibrium. If this is an equilibrium, extent of it going to the right depends on equilibrium constant, which we use K for that, because this is equilibrium constant for acids. We call it acid equilibrium constant, or Ka. You might remember that equilibrium constant is always defined as products on the top. Over the reactants. So if I am going to write equilibrium constant for this equation, products on the top, so hydronium ion on the top, concentration of conjugate base on the top, on the bottom, I have concentration of weak acids, and concentration of water never changes, it's fixed, it's constant, so I can place that constant inside this, I can hide it inside Kas. I don't have to write it every time. Remember, when you write equilibrium constant equation, equilibrium constant expression, you never write concentration of solids, and you do not write concentration of pure liquids, because they are fixed number. They're constant, they don't change. So can I then solve this equation for hydronium ion concentration? In other words, if I want pH of a buffer, I need to know hydronium ion concentration. If I take negative log of hydronium ion concentration, then I'll have pH. So in this equation, how would you solve this equation for hydronium ion concentration? How would you solve this equation for hydronium ion concentration? If you do cross multiplication, Ka times weak acid is equal to 1 times hydronium ion concentration times conjugate base. Solve that for H3O plus. This is what you're going to get. So in a buffer system, you can calculate hydronium ion concentration. And if you want to calculate pH of a buffer system, do you remember pH is always equal to negative log of hydronium ion concentration? So if I have the Ka value, concentration of the acid form, concentration of conjugate base, I can calculate pH of the buffer. That's all you need to calculate pH of buffer. I'm going to give you an example. Actually, this is one of the buffer system in our blood. This is the weak acid. And this is the conjugate base of the same weak acid. Why? Why is this conjugate base? Why is this conjugate base? Because it has only one hydrogen. 2 hydrogens in the acidic form. 1 hydrogen is lost. You get the conjugate base. These 2 are interconvertible by loss and gain of hydrogen. So they are conjugate acid base. The acid equilibrium constant, the acid ionization constant is given to you. Ka is given. What is pH of this buffer if we keep both of these concentrations, this is 0.2 and this is 0.2. These are mole per liter. So concentration of the acid base, conjugate acid base, is always given to you. Ka is given to you. You want to calculate pH, all you have to do, write the formula for hydronium ion, which is Ka times concentration of the acidic form over concentration of the conjugate base. Or in order to memorize this, is easy. Ka times A over B. Can you memorize this? A for the acid, B for the base. So the concentration of acidic and basic form here are equal together. So 0.2 on the top, 0.2 on the bottom. Ka is this. Obviously, these two cancel each other. So hydronium ion is 6.2 times 10 to minus 8. And if I ask you, how do you calculate pH? You write negative log of this value. Get the negative log, you get 7.21. So if you want to calculate pH of any buffer system, you need Ka, which we give you. You need concentration of acidic and conjugate base form. Get the hydronium ion and take negative log of it. This is something that you have done before. How do you calculate pH from hydronium ion concentration? You use negative log. Let's see if we can do a problem. Go, guys. This is the weak acid form of this buffer. This is the conjugate base of this acid. Ka is given. Would you like to do this together?
Yes, please.
Okay, so obviously what you need is hydronium ion concentration to get the pH, right? And the formula, what was the formula? It's Ka times concentration of the acid over B, which is Ka is given. So you write 4.3 times 10 to minus 7 for Ka times concentration of the acidic form is this one. So 0.2, 0 M. Concentration of the conjugate base is 0.1. So if you write this, you get hydronium ion is, this is 2, right? 2 times this, 8.6 times 10 to minus 7. And if you want pH, you have to get negative log of the hydronium ion concentration, which is negative log of 8.6 times 10 to minus 7. It should be 6 point something. Yeah, 6.07. So this is the pH. So you see, it's not that difficult. You need Ka, we give it to you. unit concentration of the weak acid, we give it to you. Concentration of conjugates, we give it to you. Get hydronium ion and take a negative log of it. And this is the solution that we did. Let me go to next slide. So what are the buffers in our body? I told you, do you remember? Carbonic acid, the acid in the Coke, and bicarbonate system, baking soda. The second system is dihydrogen phosphate. We just did the problem. And hydrogen phosphate. And proteins, there are acidic proteins which are weak acids and the salt of their acidic protein together, they make a buffer system. So our body has got three systems of continuously watching the pH of our blood for us to stay alive. And we started our chapter with this slide, where carbonic acid in our blood is formed by reaction of carbon dioxide and water. And through an equilibrium system, carbonic acid, through equilibrium, produces hydrogen ion and bicarbonate system. So if we add any acidic system which enters the blood, is going to reverse this equilibrium. Why? You're increasing concentration of the product by entering acid into the blood. This reaction goes back according to Le Chatelier's principle. Reaction is going to counteract the change. It makes more carbonic acid. And then if you look at this equilibrium, carbonic acid is going to decompose. Again, because of Le Chatelier's principle, we are increasing H2CO3. This reaction is going to be reversed. It's making CO2 and water. CO2 is going to go to your lungs and it's going to be released to the air. So adding acid to your blood is neutralized by producing carbon dioxide, which is going to come out as you're breathing out. And if we add a base to this reaction mixture, if I add base, if any basic component of the food comes into your blood, H plus will neutralize the base. So in this equilibrium, concentration of H plus goes down. The equilibrium is going to shift from left to right to make more H plus. And then in this equilibrium, if there is lower concentration of H2CO3, according to Le Chatelier's principle, this reaction moves from left to right to make more carbonic acid. So part of the CO2 coming from the lungs would be increased. This CO2 reacts with water to make H2CO3 to replace the lost H plus, which is the result of any alkaline solution, any basic solution coming into our blood. By the way, bicarbonate is being reserved in our kidney, and when this reaction wants to go back, bicarbonate is provided by the kidney. So the blue arrows shows addition of a basic reagent to the blood, which is neutralized by this buffer. The red arrows here, this red arrow and this red arrow, shows if any acidic reagent enters the blood. These are all chemical equilibrium which are going to shift to neutralize incoming acids. Amazing system, isn't it? It has got three security systems watching continuously for you and I to be alive. Three security systems backing up each other.